This video has been sponsored by Brilliant. Hello everyone! Well, I'm all out of video ideas, so let's consult the tomes. I guess that works. Water. Everyone loves water, especially me. I love water. 23 years ago, I was born in the dregs of the United States, also known as Portland, Oregon. Portland receives lots of rainfall, so the aesthetic of rainy weather and flooding streets is something my daydreaming mind reaches for most often when trying to visually construct an interesting scene. 3 years ago, when I was a fledgling graphics programmer, I dreamed of creating my own real-time fluid simulator with legitimate fluid accumulation from falling rain and accurate rain splash physics. Then I realized that partial differential equations really do have hands, and that real-time fluid simulator is a bit of an oxymoron. Unfortunately for me, I'll probably die before large-scale real-time fluid simulation is possible. But if fluid simulation is too expensive for games, then how is everyone rendering their water? If you went to school, then you know what a sine wave is, but many people lack an intuitive understanding of them, and if you're an aspiring game developer, you should start learning to love the sine wave. Thankfully, they're very simple. Sine waves are oscillators. They repeatedly move back and forth between two different values. This is useful since we know for sure that no matter what point in time we sample our wave, it will always be somewhere in between its peaks. The peak value of the wave is known as its amplitude. Since the amplitude of a basic wave is 1, we can easily change it to whatever we want by multiplying the wave by the maximum value we desire. The distance between two peaks of a wave is known as its wavelength. The shorter the wavelength, the faster the signal will repeat. In order to get a desired wavelength, we need to convert it to frequency, which is the rate at which a wave repeats every second. Thankfully, we can get our wave's frequency by taking the quotient of 2 over the desired wavelength and multiplying it with our positional coordinate. With a wavelength of 1, our wave now completes a full repetition in between 0 and 1, and if we consider the x-axis to be time, then our wave repeats every second. This is our core wave equation, but it's not very useful to us game developers without one more crucial component, the phase. At the moment, we can't animate anything with our wave because it's not going anywhere. In order to move our wave forward through time, we need to add time as a second variable and add it to the inside of our wave function. We can then control the speed of our wave by expressing speed as a phase constant. We multiply our desired speed by 2 over the wavelength and then multiply it with our time variable. Since the wave's frequency is also equal to 2 over the wavelength, then our speed parameter is in terms of frequency. It is with this basic wave equation that the secrets of water rendering are revealed to us in Chapter 1 of the first edition of GPU Gems, making use of a technique called the sum of sines. GPU Gems tells us that one wave is boring, but many waves, now we're getting somewhere. The sum of sines is fairly self-explanatory. It's a sum of sine waves. If we add 2 of the same wave together, nothing that interesting happens. But if we add a wave to a wave with different amplitude, frequency, and speed, we begin to see some more interesting patterns. The more waves we add together, the more detailed of an animation we get. With just 4 waves, we can already see some convincing fluid-like movements in 2D. But what about 3D? Over in Unity, I have a simple plane composed of many vertices. In order to see our waves, we need to displace the vertices according to the sum of sines. The easiest way to do this would be to have our CPU iterate through every vertex of the mesh, updating its position every frame. But for a plane with this many vertices, that's perhaps the worst idea you could possibly have. Instead, we'll leverage the immense power of the GPU to do our displacement for us in the first programmable stage of the rendering pipeline, the vertex shader. When the CPU tells the GPU to draw an object, the object's vertex shader is executed on every single vertex of its mesh. The vertex shader is responsible for finalizing per vertex data that will be sent to the next stages of the render pipeline, which includes finalizing the position of our vertices. This is the functionality we're interested in for the water. We have our vertex shader calculate the sum of sines on each vertex, displace it accordingly, and then send it off to the rest of the render pipeline. As you can see, our mesh is now animated with the vertex shader doing all of the work for us, and it's very fast too, especially when you compare it with the CPU approach. But Acerola, it doesn't look like water at all. That's because we still need to implement the second major stage of the rendering pipeline, the pixel shader. The pixel shader is responsible for outputting the pixel color on the screen. Right now, our pixel shader is returning white for every pixel of our water, resulting in this formless white blob. To give our water form and detail, we need to calculate how the light interacts with any given point on the surface of our water. There are many intimidating equations I could show on the screen right now, but let's start with the basic calculation that is the core of every physically based shader, the lambertian diffuse. Imagine we have a sphere with a light shining on it. If I ask you to draw in the shading, then it would probably look something like this. The points on the sphere that point towards the light are fully lit. The points that point somewhat away are less lit, and the points that point opposite to the light are fully in shadow. It's from this that we could intuit that there is a relationship between the direction of the light source and the direction of the surface, also known as the surface normal, a vector that is orthogonal to the surface. We can see that the greater the angle between these two vectors, the less the light is scattered off the surface. Conveniently, the cosine function will give us a value of 1 when the angle between the vectors is 0, and will give us -1 if the vectors are pointing opposite from each other. For simplicity's sake, we clamp the cosine value to 0 because negative light doesn't exist. But how do we get the angle between the vectors? If we look at the equation for the dot product of two vectors, we can see that the dot product is equal to the product of the vectors' magnitudes times the cosine of the angle between the two vectors. Since our light direction and surface normal are normalized vectors, their magnitudes are both equal to 1, so all that's left is the cosine of the angle. This means that if we take the dot product of our light direction and surface normal, we are given a value between 0 and 1 that describes how bright the point on the surface of the sphere should be, and we have successfully derived what's known as Lambert's cosine law. This concept was introduced back in 1760 by Johann Lambert in his book Photometria, hence why we call it the Lambertian diffuse. We've already gotten ahead of ourselves though, because if we go back to our water, you might start asking the question, where are the normal vectors? Like I said earlier, a normal vector is a vector that points orthogonal to the surface at any given point. In order to calculate a normal vector, we need two other vectors, the tangent and the binormal. The tangent vector is the tangent line of the point on the x-axis, and the binormal is the tangent line on the z-axis. The cross product of these two vectors produces the normal vector. To get our tangent and binormal vectors, we need to find the slope of our point in the x and z directions. We can easily do this the old-fashioned way by sampling neighboring points in our sum of sines height map, and then calculating the slopes with the usual rise over run formula that you learned in the 3rd grade. This method is known as calculating normals through central difference. It's a very common technique because most of the time you can't do anything better. Central difference has a number of drawbacks though. For one, the accuracy of our normals is limited by the distance of our samples. Another drawback is that it's expensive. If we aren't pre-computing our sum of sines into a texture, then in order to calculate our central difference, we need to recalculate the sum of sines 4 extra times to get our neighboring samples. So basically, we're doing a lot of extra work to get a normal vector that's an approximation and doesn't always look good. Normally, I'd say this is the best we can do, but for once, that's not the case. In fact, we can get pixel-perfect normals by making use of the power of calculus. As a quick recap, we are creating our normal vectors through central difference, which means we are estimating the slope along the x and z axes. But why would we estimate the slope when we could just calculate it? So far, I have been using the word slope to avoid the use of the word partial derivative, but that's exactly what we've been approximating, the partial derivatives of our point. Since the surface of our water is defined by an exact function for once, this means we can use calculus to find the exact partial derivatives of our water. For a single wave, the derivative of sine is cosine. To get the partial derivative, we multiply the cosine by the direction of the wave and the axis we want. Then we construct our tangent and binormal vectors and take the cross product to create our pixel-perfect normal vectors. Now all we have to do, if you remember from earlier, is take the dot product of our normal vector with the direction of our sun, and we have successfully calculated the Lambertian diffuse. But, Mr. Rolla, what about the normal vectors for the sum of sines? What a great question. It turns out that the derivative of a sum is the sum of the derivatives, so we just calculate the derivative of each wave and add it to a sum as we go along to get our partial derivatives. With calculus, our normals are now exact, not an approximation, and we're doing half the work, so we are using less resources. It's a total win-win. We can change the color of the water by multiplying the diffuse term with any color we want, like blue. Wow, look at that beautiful water. You know, many Acerola viewers ask the question, how do I become a graphics programmer? Well, hold your horses, partner. Before you learn to program a graphics, you've got to learn how to program in general, which is why I'm excited to tell you about a free and easy way to get started on your educational journey. Brilliant is the best way to learn math, data science, and computer science interactively. Brilliant offers thousands of lessons, from basic to advanced. So if you're just getting started learning math, or are brushing up on your linear algebra for shaders, Brilliant has something for you. Don't know what your skill level is? Brilliant customizes content to fit what you need. Just take a quick quiz when you sign up, and Brilliant will match you with lessons that fit your interests and level of expertise. I was privileged enough to have a formal math education, but my last math class was 4 years ago, so I've been taking advantage of Brilliant's math lessons to refamiliarize myself with the basics of calculus. Their lesson plans let you go at your own pace, and I'm the kind of person that has to read something 20 times over to understand it, so I appreciate that a lot. Be sure to try out everything Brilliant has to offer with a free 30-day trial and 20% off an annual plan when you visit brilliant.org/Acerola, or click the link in the description. Thanks so much to Brilliant for sponsoring this video. Now, let's make the water actually look like water. The Lambertian diffuse is just one piece of the lighting puzzle. It models the light that is scattered in all sorts of directions after hitting a surface. But there's one more important thing that happens when a light ray hits a surface. Some of it reflects. Light rays from a source that reflect directly into your eyes are not just annoying, they are also referred to formally as specular reflections. So how would we add them to our water shader? Imagine a point on our water. We know its normal vector, we know the direction of our light source, and we also know the direction we are viewing the water from. Since these are reflections, then intuitively the specular highlight should be strongest when our view vector aligns with the reflection vector from the light source. We can very easily tell if this is the case by calculating a half-wave vector between the view and light vectors. If we then take the dot product of the half-wave vector with the surface normal, we'll be given our specular highlights. But why does this work? If you recall from earlier, the dot product of two normalized vectors is the cosine of the angle between them, and if that angle is 0, then cosine outputs a 1. If the view direction is the same as the reflection vector of the light direction, then their half-wave vector will be equal to the surface normal, giving us a dot product output of 1, meaning a full-strength reflection. We can then control the size of our highlights by putting an exponent on our dot product. This model for specular highlights is the most well-known and most common method known as the blinn-phong specular, proposed in 1977. In fact, the combination of the Lambertian diffuse and the blinn-phong specular, along with a constant ambient light value, is the most basic and introductory lighting model for physically based rendering, which video games used for a very, very long time. With specular highlights, our water is one step closer to looking like actual water. But at this point, we're no longer held back by our lighting. Instead, we need to bring our water animation to the modern era. The sum of sines method presented in GPU Gems is a great baseline. It's perfect for small bodies of water that are not that turbulent, where too much detail would look unnatural. The basic sine wave works great here, but if we want to model waves with sharper peaks like that of real-life waves, we need to make some modifications to the sine wave. The sum of sines in reality is just a sum of any kind of wave. We could use cosine if we wanted to, it really doesn't matter. So any modification we make to our sine wave, the behavior remains the same. We create a bunch of them and then add them all together. There's infinitely many variations of the sine wave to give it sharper peaks. The one you are probably most familiar with is the gerstner wave, but I'm personally not a fan of them as they are really hard to work with. They're overly complicated and the parameters of the gerstner wave are very finicky, meaning it's easy to create a wave that curls in on itself, which completely ruins the visuals. Instead, I'll be making use of a much simpler variation of the sine wave where the wave is the exponent on Euler's number. As you can see, we have sharper peaks and wider troughs like you would expect a water wave to have, and we can easily control the size of the peaks without fear of it accidentally ruining the visuals like gerstner waves. This does complicate our derivative a bit more, but that's to be expected. With our new wave equation, the sharper peaks are immediately pretty obvious and add some nice detail to the water, but our sum of sines is suffering from one other major issue. If we want more detailed water, then we need to add more waves, but adding more waves leads to some very ugly visuals without compensating by reducing the amplitudes of every wave. In order to fix this, we're going to make use of one of the most important algorithms in graphics: fractional Brownian motion. Brownian motion is the term we use to describe a movement that is completely random. At the moment, our sum of sines could be considered Brownian motion, since we are summing up a bunch of random signals to create what is effectively white noise that happens to vaguely look like fluid movement. Fractional Brownian motion, on the other hand, is very similar, but instead of being entirely random, there's some memory to the process. It's kind of hard to explain, so let's just get into how it works. We start with a wave with an amplitude and frequency of 1 and a random direction. We sample our wave, add it to a sum, calculate the derivative, and add it to a different sum, just like we've been doing for our sum of sines. But now, unlike before, we are going to multiply the current frequency by a number greater than 1, like 1.18 for example, and multiply the current amplitude by a number less than 1, like 0.82. Then, on the next iteration of our loop, we use the new frequency and amplitude for the next wave that has a new random direction. We can do this for as many waves as we want, but eventually the amplitude is going to approach 0, so adding more waves won't do much. That's precisely the point though. We start with a big wave, and we are iteratively adding a wave of higher frequency, but with a smaller amplitude each time. These higher frequencies are going to be the source of our finer details, but will have less and less of an impact at higher wave counts in order to prevent complete chaos, like with our normal sum of sines. The fractional Brownian motion allows us to easily control how detailed we want our water to be. At lower wave counts, we have a more stylized look that's similar to the basic sum of sines, but at higher wave counts, we have very fine details with precise normals that makes for a convincingly realistic looking surface. Is it actually realistic? No, not at all. But people are very bad at identifying realism, myself included, which is why I spend 75% of my time staring at random light interactions around me and asking myself the question, if I saw it in a game, would I think it's realistic? And the answer is usually no. Anyways, the last thing we can do to improve our water animation is something called domain warping. While we're summing our waves, we can push the position we are sampling our wave at by the derivative of the previous wave. That way, it's almost like the waves are pushing each other around. It's a very simple change, but it makes a huge difference. Our water asset is finished. Now, it's time to make it look cool. A large body of water requires a large plane, so let's heavily increase the size of our water. We set the ambient light, diffuse light, and specular highlights to appealing colors. Then we spend the next hour fiddling with the water parameters to get a nice animation. The horizon cutoff on the water looks ugly. We fix it by applying a distance fog post-process. We attenuate the distance fog based on height to make it look more like atmospheric scattering. These specular highlights look unnatural because there's no sun to go with them. We can create a fake sun by taking the dot product of our view vector with the sun direction and additively blending it with the source. Then we can find a skybox off the internet to get a better looking sky. The skybox is going to do wonders for our water because of the beautiful environment reflections. Wait a second. I forgot the reflections. The appearance of water, especially still water, is almost entirely composed of reflections. Without them, our water won't really look like water. When it comes to real-time graphics, we have 3 general options for reflections. The first is ray tracing. Ray tracing gives perfect reflections, but it's extremely expensive, and I'm still working on a 1660, which doesn't have any ray tracing hardware, so clearly this option is not valid. The second option is screen space reflections. Gamers love to complain about bloom, motion blur, and other effects, but what they should really be complaining about is screen space reflections. This is by far the worst image effect that is commonly used in most games today. Screen space reflections are a complete and total sham. They are extremely unrealistic, and if you know how to break them, and it's really easy to break them, it immediately destroys the visuals of the game. This is because screen space reflections can only reflect what is currently on screen. So if something that is being reflected moves out of view, the reflection disappears. Here's an example from Final Fantasy XVI, which came out just a few weeks ago. The only reason they are used is because they're the cheapest option by a very wide margin, and if you don't know any better, then they look convincing. So I'm sorry for ruining it for all of you. The third and final option is image-based reflections, where we make use of cubemaps to store environment data, which we then sample from to determine our reflections. Wait, What is a cube map? A cube map is a combination of 6 different textures projected onto the sides of a cube. Instead of using 2-dimensional UV coordinates like normal textures, we use a directional vector which points at the pixel we want from the cube map. Our skybox is a cube map composed of these 6 textures. We are using the camera's view direction to sample it. We can then very easily render reflections on the water by calculating the reflected vector from the camera and using that to sample our skybox. This immediately makes our water look much better, but it's not quite correct yet because we aren't taking Fresnel into account. Fresnel describes the relationship between the angle of incidence and the strength of the reflection. Essentially, surfaces exhibit much higher reflectance when viewed at near grazing angles. This is something you observe every day of your life, but now when you see it, you can point and say, wow, fresnel. A decent approximation of Fresnel for real time is the Schlick Fresnel, which looks like this. I'm not going to explain the math, but basically, if you are looking down on something, then it exhibits very little reflectance. But if you are looking at something at a grazing angle, the reflectance is very high. This phenomenon also applies to specular reflections, so make sure you're multiplying your speculars by Fresnel. Okay. Where was I? The skybox is going to do wonders for our water because of the beautiful environment reflections. The static skybox looks weird. We can animate the UVs and blend the skybox with itself in order to create the illusion of moving clouds. The sun is supposed to be bright, but it doesn't feel bright, so let's add a bloom pass. The bloom pass pushes our render into HDR. We can use a cinematic tone mapper to bring our values back down to get some beautiful contrast at the same time. We finish up our effects with a subtle vignette and complete the scene with some calming ocean ambiance. In the end, the sum of sines, or fractional Brownian motion, is the secret behind the water rendering of most of the games that you play because it's cheap and effective. You might ask the question, how can you say something like that with such certainty? Well, if I lift the camera up above the water, then all of you will go, oh. The unfortunate truth of this technique is that it suffers from the dreaded tiling patterns that we all hate to see in games like Pokemon Legends Arceus and even Elden Ring. We can remedy the repetition by adding more waves, but because waves are oscillators, the patterns will always repeat eventually. This means that you should only use this approach for small bodies of water or coastal views where the player is unable to see the repetition as easily, like I have so expertly done in my demonstration. Other games like Sea of Thieves have remedied this issue with much more sophisticated fluid simulation techniques. That's for another time in another video. If you would like to support me and keep the channel going, check out my Patreon. All my patrons get to vote on the next video topic, and while the next video topic has already been decided, you'll be able to vote on the next one. As always, a huge thank you to all of my existing patrons. Without your support, I would not be able to eat Taco Bell 21 times a week. Also, I'm streaming right now over on my Twitch channel. I'm building a Lego typewriter. If you have any questions about the video, come hang out and chat. Anyways, that's all from me. I hope you have a great rest of your day, and I'll see you next time.